back, welcome back, welcome back. I'm Lisa Blackburn, and this is my YouTube channel for everything I like to talk about science and math. And today we are in chemistry class learning about atoms in the periodic table. So everybody in class who's out can watch it later today. Yay. All right, so you notice we have a cute little guy here. We're going to learn about atoms in the periodic table, and in particular, we're going to learn a little bit about the history of chemistry. So there'll be part on the test where you match the person to what they did. So make sure you learn them, okay? So the very first person, going way back to the history of chemistry, is a Greek guy. This makes really good TV when I wander off the screen, doesn't it? All right, anyway, it was a Greek guy right there, and he gave us the term atoms. His name was Democritus, and he gave us the term atoms. And this is how he did it. He was not a scientist, he was a philosopher. And he was standing on a beach one day, and he said, this beach is one thing, but it is made out of many things, the little grains of sand. I am one thing. I bet I'm made out of little pieces. I'm going to call them atoms, which means indivisible. He was ancient Greek philosopher. So when you say the Pledge of Allegiance, you can say, one nation, atoms for liberty and justice for all. It means indivisible. So the idea is everything is made of atoms, like a beach is made of sand. Aristotle came along, and he said that matter is uniform. Do you have that on your page too? Sometimes I add stuff and I forget to add it to yours. So anyway, that was sort of the beginning of chemistry way back then. Then way later, 1700s, it sort of came back. Now, there was a period there where we didn't have real chemistry, but we had alchemy. So this is the witchcraft dark past of chemistry. There was a period like in the Middle Ages where they were trying to use witchcraft and spells and potions, and that's where the real chemistry came in. And one of the ideas is to change lead into gold, get rich quick using witchcraft, okay? So, but the alchemists actually did a lot for us. They came up with a lot of the glassware we still use, some of the techniques we still use today. So it's not like nothing was happening till John Dalton, but that what was happening was not very scientific. Does that make sense? It was kind of... Yes?
Miss Blackburn, will you send Keelan Martin to the office for a moment?
Yes.
Thank you.
You go too and get your glasses. Okay. All right. So John Dalton was the guy who sort of brought it to the scientific age, and he came up with the atomic theory of matter. Okay, so he is the one who brought it into the modern age, and he came up with this theory. Now, theories in science are different than theories in common speech. Are we going to talk about that here or later? We'll talk about it here. In common speech, I can say, I have a theory about that. And it could be something crazy. Like, I used to have a theory that nobody liked fruitcake. They just gave it to each other, and then they re-gifted it. And maybe all the fruitcake ever was made in the 1950s. And since then, we're just re-gifting it. But then I met a student, and she said, oh, no. I like fruitcake. And if you had my grandmama's fruitcake, you would like it too. Her homemade fruitcake is just great. So that blew my theory. Now, was my theory very scientific? Not at all. So in science, a theory is true but changeable. So we're going to talk more about that later. But he said this is the atomic theory of matter. It's basically true, but there were parts of it he had wrong, and we've changed it. But we still agree that things are made out of atoms. We're just changing it as we get more information. As opposed to a law in science. A law like the law of gravity is so true it's math. So that's the difference. Did you check in? You have a pass. All right. I'll have to remind me to correct the attendance because right now you're out. Okay, so this is what he thought of. All matter is indivisible and made of indestructible atoms. That's point one. Point 2, Maria, the notes are over here for you to pick up. Atoms of a given element are identical in their physical and chemical makeup. Atoms of different elements have different physical and chemical makeups. So that's identical and different. I know it's hard to read. I should have had bigger blanks. Atoms of different elements combine in simple whole number ratios. Whole. That little blank is whole number ratios to form chemical compounds. Atoms cannot be subdivided, created, or destroyed when they are combined or separated in chemical reactions. Now we know a little bit more about it. So that's not exactly right, but it was a great start. So his is called the billiard ball model. He said that atoms are like little balls. So you also on the test will need to match the guy to their model, the name of the model and what it looked like. So his was the billiard ball. So in case you don't know what a billiard ball is, it's like pool, but there's no holes for the balls to go in. They just bounce around. I don't know how to play it, but there's a way to play pool with no holes in the table. Okay, so that's what he called it. He said, so it's like a pool ball. Okay.
Miss Blackburn,
Yes.
could you please send Michaela home up for checkout?
Yes.
Thank you.
You're welcome. We just have a lot of people going to the office today. These notes, Michaela, will be on YouTube. Okay. And right now the old ones are. Okay, so any questions about that? With all those interruptions? All right, so I am going to scroll this. Can we scroll? Am I good to scroll? Ball. It's the billiard ball model. Can't hear you even a little bit. What? Reaction? Reaction ball. This is just going to make really good YouTube. I'll probably be like YouTuber of the Year award for this one. Okay, so our next guy is J.J. Thompson. And he came up with, let me tell you the story of him. Okay, so a lot of times technology goes before science. And they said that in that video we watched, Element, the mystery element, the ones that worksheet that was in your packet this time. A lot of times technology happens first and then that opens up science. So they had this ray gun. How cool is that? And it could shoot beams, rays. And they noticed that they were shooting their ray gun and they took a magnet up to it that you could make it go right or left depending on which end of the magnet it was. So they figured out there was something in the atom that had a charge. Do you see that? So because of that, J.J. Thompson came up with the plum pudding. Now, plum pudding was a dessert a long time ago, and you can think of it like Jell-O pudding with raisins in it. She got her glasses. But it wasn't really like that. You know how in England they call all dessert pudding? If you ever heard the Pink Floyd song, you don't get any pudding if you don't eat your meat. That's a very old song, before my time, so it's before your time too. But I still see the Pink Floyd Dark Side of the Moon t-shirts in the hall here, so you might have heard the song, okay? So, because I think it's off of that album. Anyway, so, but you can think of it like pudding with raisins in it. Plums or prunes, plums, okay. So they decided that's what the atom was like. It was like this, where it has got this negative goo with positive little raisins in it. So imagine you've got a bowl of Jell-O pudding, vanilla, and the yellow vanilla pudding is all positive, and the negative, and you put raisins in it, or chocolate chips would taste better, that those would be the negative part of it. That was his idea, okay? Because something was positive and negative. And how they figured this out was a cathode ray tube. How cool is that? The particles can be attracted or repelled by a magnet. And so the plums were the negative charged electron and the pudding was the positive goo. Now, so here's our ray gun. Okay, so that was J.J. Thompson. So Ernest Rutherford was friends with J.J. and he wanted to prove him right. He wanted to prove that he was correct. So he did an experiment. And what he did was called the gold foil experiment. And this is how it worked. He had a room that had glowing stuff that glowed in the dark when it was hit with the ray gun. Okay? Every time the ray gun hit it, it glowed in the dark. And then he put a piece of gold foil. It's just like aluminum foil, but made out of gold. And because gold is very malleable, whoever did the report on gold said that, meaning you can hammer it really thin, much thinner than aluminum foil, that only to about 10 atoms thick. He put a piece of gold foil and then he shot the ray gun at it. So if you took a gun and shot it through pudding at a wall, what pattern do you think you would get on that wall? A big splatter, right? Big old splatter. So he was going to prove that JJ was right by the glow-in-the-dark splatter. That makes sense? He was so confident JJ was right, he didn't even show up to the experiment because it didn't sound very fun. Being in a dark room, counting how big the splatter is. So he just made his graduate students do it. That's not what happened at all. So what happened, this is called this is the famous gold foil experiment. And because that didn't happen at all, he had to come up with a new model, and it was called the planetary model. Planetary. So you still see this. You still see I call it the Jimmy Neutron model. Well, one way to look at it is kind of like this, and it's like he decided instead it was like planets going around the sun, okay? So, but this is what happened. When he shot the pudding, when he shot the atoms, those were the pudding, the gold atoms, 99.9% of them went straight through. Every now and then one would get deflected over to the right or the left, or even notice how the glow-in-the-dark stuff goes almost all the way around. Some of them came straight back at it. Ernest said he could not have been more shocked by this result than if he had taken a piece of tissue paper and shot a shotgun at it, and everything he shot out of the shotgun come back and shoot him. This was just as shocking. Can anybody figure out why this was so shocking to him? Why he was absolutely blown away by this result? Do y'all understand why it's so shocking? What's shocking about it? What stopped the ray gun? 90.9%, what stopped the ray gun? Nothing. Nothing. So what it meant and why it's so shocking and why you should be shocked too is that 90.9% of everything is nothing. You are nothing. Sorry to depress you today, but 99.9% of you is not there. Matter is mostly empty space. The ray gun was going through empty space. Every now and then it would hit something and get deflected, but the majority of everything is nothing. But that's okay. You knew there was more to you than the atoms that make you up, right? You've got spirit and soul and creativity. So don't be depressed that you learned that you're nothing today in chemistry class. Okay? So that's why it was so shocking. Now, are you a little shocked too? The only thing that stops one hand from going straight through the other one is energy. It's not really matter, it's energy. Are you a little shocked? You got a little of JJ's wonder at this? Ernest about JJ's thing? All right, let's scroll again. Find my scroller. Okay, so this was shocking. I'm gonna see if I can go a little higher. No, not that far. That's good. Okay, so why was it shocking? Whoop, page 2. It's because the atom is empty space. The atom is empty space. 100,000 to 1. Now, I've heard different statistics on this. You can look up most current ones. One I've heard is that if this room was an atom, The nucleus, the only part that's got any substance to it, the only part that's got any matter, would be a printed dot on your page. All the rest, empty space. I've heard it said that if the nucleus was as big as a baseball, then the atom would be as big as SunTrust Baseball Stadium. Empty space. But I've heard that that's wrong. That the nucleus was as big as an atom, as a baseball, and we had it here, that the atom would be Dallas, Georgia. But either way, it's empty. The atom is empty space. There is nothing there. Now y'all can be shocked, along with Ernest Rutherford. So what he figured out was that there's something inside. It's not the pudding, but instead there's a nucleus. And nucleus is Latin, just like how atoms means indivisible. Nucleus means little nut. That says little nut. If I don't pick my finger way off, it writes when I don't mean it to. It looks like hiddle nut, but it's little nut. Okay? So the next guy coming along, that was Niels Bohr in 1913. Electrons, he figured out, can only hang out in certain energy levels. Big E is science shorthand for energy. Energy is so important. Everything always comes back to energy. Whenever you have a question in chemistry and you ask why, usually the answer is energy. It's just the answer. Okay. Electrons can only hang out in certain energy levels. They jump between the levels, and that jump takes a certain amount of energy called a quantum. Have you ever heard of a quantum leap? There used to be an old show in the 90s called Quantum Leap. I don't think it had anything to do with this. But students would always ask me, Miss Blackburn, have you seen Quantum Leap? It was about a time traveler, I think. I've never seen it. The guy had a mullet. That's all I know. Mullets are back. Okay, so he is the one who figured, okay, so this is the other way of the other model that came out of Rutherford's. Electrons circling the nucleus. So what Rutherford thought about, going back to him, was space is empty. We have the sun, and then we have the vastness of the solar system, just emptiness, and the planets going around it. So he said, okay, so that must how it is, that we must have a nucleus like the sun, and then the electrons that there are patterns in nature, and this must be reflecting that pattern. And that's just true. There are these patterns in nature that you see from the small scale to the big scale over and over again. For example, the mathematical equation for a spiral is very advanced. Very, very complex. You will not learn it in Algebra 2. It's going to be pre-calculus before you learn this math. Very advanced. And we see that very advanced math on a snail shell, in a shell that's like a conch shell that you listen to at the ocean, and you see it in galaxies. So this same pattern is throughout creation, from the small to the great. So we even see that pattern in galaxy clusters. So this mathematical complex thing you can see everywhere. So knowing that, he applied planets to the atom. And I always think of that as the Jimmy Neutron model, because that's what you still see a lot for atoms. I have a t-shirt that I would wear if they were letting us wear t-shirts this year that has that on it. I'll try to figure out how to get to wear it. Okay, so then in 1913, Niels Bohr came along and said, that's not right, because these are all the same distance from the nucleus. Atoms hang out different distances from the nucleus. Okay, so he figured this out. And he also figured out that they don't go slowly between levels, they jump. Okay, there are no stairs between the levels for the electrons to hang out on. They jump, and that jump is called a quantum leap. We good with that? Don't you feel smart learning this? This is good, smart stuff. Okay, so that's the Bohr model. That's what this is on my board. You're going to learn how to make those for this test. See, you've been wondering about that, haven't you? What that's up there for? Unit 2. We're going to do it. Okay, so the next person who came along were the Curies. But this isn't Marie and Pierre. They figured out about radioactivity, radium, polonium. You learned that in the video we watched. This is her daughter. And his daughter too, their daughter. She had more than one girl. One became a famous movie star. and the other one became a famous scientist. I don't know anything about the movie star, but I know about the scientist. This is Irene. So her daughter, Irene Curie, and her husband, Jolet, and their lab partner, Chadwick, figured out there was something more to the atom, that there's another thing besides the positive protons and the negative electrons. There's a what? A neutron. What charge does the neutron have? No charge, it's neutral. So they figured out there's another particle the same size as a proton, but neutral. So yay! Marie, not only she an amazing scientist, first woman to ever get to speak to the men scientists, but amazing mom, had an amazing scientist daughter too, who's in the books. How cool is that? Okay, so they figured out the neutron. So the next one is the more modern view, and it's not really one person, it's a bunch of people. It's all the modern scientists now that, well, came out after these guys, and it's the electron cloud model or the quantum theory. One of the really important people is Heisenberg. So if you've seen Breaking Bad, his which I don't recommend to adult for y'all are all too young to watch it. But anyway, it's about chemistry, and his gang name is Heisenberg, and Heisenberg had a lot to do with the modern view. So we're going to talk about that view, but his principle, why the Breaking Bad guy took that name, does it have to do with what we're about to learn right now? The modern thought theory is that electrons can be thought as particles or waves. So there's a dual nature. I say it's a superhero, like Shazam. Shazam can be he can be the teenager, or he can go Shazam and he can become the superhero, right? Y'all saw that movie? Maybe not the best superhero movie, but still a good one. Okay, so anyway, electrons are like that. They can be like a particle or they can be like a wave. They have a dual nature, like a superhero. There's a relationship between electron energy and light. And we're going to do all of Unit 3 about this. Unit 3 is where we're going next, right here, in our standard. Right now we're doing Unit 2. Okay, but light here that we're talking about is not just visible light, it's the whole electromagnetic spectrum. The way I remember it is Ronald McDonald is very ugly, extra gross. Radio waves, microwaves, infrared, visible light, UV light, X-rays, gamma rays. Ronald McDonald is very ugly, extra gross. All the light, X-rays, gamma rays, radio waves, the waves that make your cell phone go, that's all light and all part of this. Here's my thing. Doop, doop, doop. Hold a second. Let's see what time. Okay. All right. So next, so that's the atom. And we're going to go into more detail with it. And we're going to see a great video on it. Anyway, Monday probably. So when I got on the thing down. Okay, now Dmitry Mendeleev. So some of y'all had to pronounce Mendeleevium, but Dmitry Mendeleev. He was in our video. Remember the Russian guy? And this is what he figured out. Now, remember how I told you a lot of the fathers of chemistry were Christians. They were trying to learn more about God. All of creation declares the glory of God. A lot of them were ministers. Not Dmitry. He was a Russian student, but one of the things he did, a lot of like the more Protestants around here wouldn't have done, is playing cards. People used to consider playing cards immoral, but Dmitry, drinking the vodka, playing the card, grad student, going to the bars, he started noticing there were patterns in the elements. These repeatable patterns are in the elements. And he set out to discover the pattern, remember in the video, because he was writing his second textbook because he needed some money. He's looking for the money. He needed to make the bucks here. So he wrote all the information. He actually used playing cards, and he like put paper on them, and he wrote the information, and he rearranged them till he found the pattern. So what he did not invent, he discovered the periodic table. And this is how he did it. he found that there are repeating predictable patterns if you arrange the elements correctly. And he did in a weekend, remember? He arranged them by atomic weight, so it wasn't completely correct because they didn't know about the protons when he did it. He discovered the periodic table. Notice I didn't say he invented it, he discovered it. The patterns have always been there. They're part of creation. The periodic table is based on math. It's based on energy. That math has always been behind everything. Does that make sense? And he figured it out. And he did it so amazingly that he left blanks for things that he knew they're going to discover an element. It's going to go right here. It's going to have these properties. Then they did, and it blew everybody away. It was like he was magic. He was predicting the future. He was predicting elements that hadn't been discovered yet. And remember on the video that he had predicted an element would have certain characteristics, and the guy who really discovered it, published it, had a different characteristic, and he wrote them and said, check it, because it doesn't go with my prediction. And he was right. The guy who discovered it was wrong. So that just convinced everybody that he was right, and he discovered the periodic table. But he wasn't completely right, because he arranged it by atomic weight or mass. Then came along Henry Moseley. He was a young cute fella, a young college student, and he rearranged it by atomic number. That's the whole numbers. We can't see ours because some people have not taken the test yet. Oh, I've got one right here. Can't be too far away from the periodic table. All right, see these whole numbers right there? That he rearranged it by those numbers, not the little decimal numbers underneath. Mendeleev, decimal numbers underneath, Moseley, whole number on top. Because they didn't know about those whole numbers yet. Those are the number of protons. Now, his story. He was a cute, young, handsome British graduate student and figured this out. World War I broke out and he got drafted to go to the war. All of his professors said, no, he's too smart. He's England's national treasure. He's smarter than us. He's probably the smartest person who's ever been born. He was probably smarter than Einstein, okay? But we don't call people Moseleys when we're smart. We call them Einsteins, and this is why. Do you think the government of Britain listened when all his professors said, no, don't send him to war, he's too smart? Do you think they listened? No, they sent him straight to the front lines. He died. Then the government went, oops, probably shouldn't have done that. And they have a law. There is a law in England that if you are super smart, you do not get drafted to go into war where you will get blown up. So that's what happened to Henry Moseley. You can see his picture. He was a cute young thing. Okay, let's go on. So we need to know the song. So there's a song to help you learn about Dmitri Mendeleev. Y'all ready?
Yes.
You have part of it, okay? I'll go through it and then y'all can join in when you're supposed to. Who told the elements where to go? Mendeleev. That's your part, okay? So we'll try that part. Whenever I do this, you just say Mendeleev. This is based on back in the 1800s, people would go to bars and drink. They didn't have ESPN to watch on the TVs or anything, so they would sing songs. So there were bar songs. And he liked to go to the bars. Mendeleev, remember, he's our party man. And so this is our 1800s bar song. And where you would know this is from Beauty and the Beast. Remember, no one spits like Gaston, no one something like Gaston. That's that same thing. That's the old 1800s bar song, okay? So this is based on the 1800s bar song, and it's the Mendeleev song, okay? You ready for your part? No alcohol required, okay? Who told the elements where to go? Mendeleev. Who put them down in columns and in rows? Mendeleev. This is the touching part. Who was willing, who was able to make a periodic table? Who told the elements where to go? Mendeleev. Okay, y'all gotta do way better because we're gonna do it till you get it right. Ready? Who told the elements where to go? Mendeleev. Who put them down in columns and in rows? Mendeleev. Who was willing, who was able to make a periodic table? Who told the elements where to go? Mendeleev. Yay! Good job. Round of applause for everybody. Now you're all going to remember Mendeleev. Okay. Let's keep it going. We have to go fast because there's a pep rally today. We don't get our usual long time. Did y'all know that? We have a shortened period. We get out at 49. Oh, the pep rally's tomorrow. That's right, it's tomorrow, Friday. We're still got to get through all this, so still moving fast. Pep rally's tomorrow. Tomorrow we have to move fast. We're going to the computer lab. We might go at the beginning. We'll probably go here and then go down there. We're going to go do things, but we want to get all this done. Okay, very good. Okay, next guy. So the next person who had something to do with the periodic table was Glenn Seaborg. He was alive in the 80s when I was a teenager. So I remember seeing him like on TV. You know how like there are certain scientists that they'll always interview on TV whenever anything sciencey happens? He was the guy in the 80s. Now it's that, what's the guy's name? Neil deGrasse Tyson, what's his name? Okay, that Glenn was him. Okay, he was the one they would always interview. So I remember seeing him on TV. Anyway, so Glenn Seaborg, what he did to the periodic table is he rearranged it by putting the bottom section. Oops. He did the bottom section. Come on. He did the bottom section. So this is called the actinides and lanthanides. You know what? We're just going to call it the bottom section because I'm going to tell you actinides and lanthanides on the last page. We don't have to know it now. So you know how there's that little part down at the bottom of this? Glenn Seaborg. He figured out to pull those out. And then we got it. All the people worked on discovering it. Mendeleev, Moseley, and Seaborg. So they discovered the periodic table. Okay, now the story of radioactivity. This is what really excited early chemists was learning about radioactivity, which you learned in that video about Marie Curie. Okay, so it started with Henry. I always wanted to call him Henri Becquerel, and then I thought, well, it says Henry, so I started calling him Henry. But in that video, they called him Henri. So we're going to call him Henri again. Henri Becquerel. He accidentally discovered radioactivity. And they talked about this in that video. Y'all remember how he accidentally discovered it? This is how. Radioactivity. I left out the V. Radioactivity. Okay, so how he did it is he was investigating glow-in-the-dark rocks. So glow-in-the-dark rocks, y'all have seen glow-in-the-dark, right? You hold it up to the light. You turn out the lights and it glows. And what he was seeing was, do glow-in-the-dark rocks glow bright enough that I could use it to take a picture? Because photography was new back then. Do they glow bright enough that I could take a picture just by the light of the glowing rock? Okay, you following his experiment? So he was done for the day. And so he was cleaning up. It was Friday, quitting time. And he took his glow-in-the-dark rocks and he put them in a drawer with some new unexposed film. So y'all are all the digital age, but you used to be able to buy film at the drugstore and put in a camera. You know, like the Polaroids, those are sort of back, where you take a picture and the picture comes out. It was a lot like that. It was like the film, but it hadn't been used, like the Polaroid film. Okay, he put it in the drawer and ready to work on Monday. He comes back, gets out his new film, and it's all been exposed. He said it was like somebody held it up to the sun, totally ruined it all. But it had been in a dark drawer all weekend with these rocks. Well, normal glow-in-the-dark rocks do not glow once the light is taken away, right? They don't glow anymore, regular glow-in-the-dark stuff. Turns out his rocks had uranium in them. Uranium is radioactive. It always glows. It's how you knew that was not uranium on my desk. I wasn't giving us cancer. If you picked uranium, you picked wrong on the test yesterday, because I'm not getting out uranium giving us all radiation poisoning, okay? So he had these glow-in-the-dark rocks. They are on accident they happened to have uranium in it, and they had exposed the photographic plates with some mystery ray. He didn't know what it was called, so he called it X-rays. He could have called it Becquerel rays, but he didn't, out of modesty, just like Amadeo Avogadro. But we named the unit after him. They are called becquerels. So we went back and honored him for discovering this. So he discovered X-rays, and they had a blast with them. They started taking pictures of broken bones. You saw where they took a picture of a lady's hand with a ring. They took pictures of animals. They had the best time with X-rays and photography plates. They had no idea that they could be harmful. My mom was a kid in the 40s, and she said that they used to have shoe stores in Atlanta where you would go and you would stick your feet in an X-ray machine, and they would X-ray them to get just the right size shoe for you. There is no way they would do that now. Think of all those poor people selling shoes with that X-ray machine going all the time. You know they died of cancer. So anyway, they had a great time, had no idea it was harmful. Okay, so a friend of Becquerel's was Marie Curie. And she was the first person to really understand radioactivity. So her and her husband, this was another one where technology came first. Pierre was really good with the technology stuff. She was real good at understanding it. And we saw that in the movie. Remember the video we saw? Okay, so they had discovered a lot of stuff. And back then, the center of learning for the world for science was Paris. So they had an academy that you would come and present your findings to. Well, Pierre was supposed to go tell them the findings, and he got killed. He was hit by a taxi cab on his way to present. Now, this was back when it was at the time of cars, but they still had a lot of horses. You know how in big cities, you could get the horse to haul you around. Even Marietta, you could get the horse to take you around. Well, this was Paris, so it was one of those horses that could take you around the city. They ran over him and killed him. Well, then she was the only person who knew the research. So they had a rule: no women. Women can't talk, and they changed the rules so she could come present. So yay, Marie Curie, changing society there. So her husband died. He was hit by a taxi cab. So she was the first ever woman to speak to the scientific community. She discovered the elements radium and polonium. She did a lot. Okay, so next in our story, another woman, Lisa Meitner. Now, I've heard her said Lisa. I've also heard people call her Lisa. We're sticking with Lisa. I'm sure I'm saying it in perfect German anyway. All right, so we got to go back to scrolling. See, don't y'all think this is kind of interesting? I think the stories are interesting. Miss Weeks says she hates this part of chemistry. She doesn't like the stories at all. I like the stories. All right, so Lisa Meitner. So this is World War II. We're jumping forward to World War II. Germany, Hitler, okay? Get your mind to the right place. She was working with two other scientists, Otto Hahn and Fritz Strassmann, and they were working on radioactive elements, trying to understand them. Lisa was Jewish. That's a problem in World War II Germany, right? Okay. So they realized that they needed to get her out. So Otto Hahn and Fritz Strassmann, they were not Jewish, they were just German, and they all pooled their money, sold their jewelry, and smuggled her out to neutral Switzerland. They got her out of there. They saved her life. Yay! Okay, so she couldn't work anymore. She's in Switzerland. They're still doing the work, and they're sending her their results, and they are getting these results they don't understand because it's just so weird that they start with one thing, and then they end up with that thing going. They're shooting it with the gamma rays, and then they start with one element, and then they get these other elements that aren't even close to that element on the periodic table. It was very confusing. They sent her their research. Okay, now she was Jewish by ethnicity, Christian by her religion. Does that make sense to you? So just because you're Jewish, you don't have to be the Jewish religion. You could be the Jewish religion without being the Jewish ethnicity. Do you think Hitler cared? No, he didn't care. He didn't care what your religion was. He'd just kill you. Okay, so they got her out. She's celebrating Christmas, so that's what always confuses people. She is celebrating Christmas, which Jews don't normally celebrate. So she's celebrating Christmas, and her nephew comes for Christmas, and she gets the lab reports from her lab partners, and her and her nephew going over it, she figured out what happened. They had split the atom. She figured out they had split the atom. So they shot it with alpha particles, they split it. This is nuclear fission. Nuclear fission. Nuclear fusion is putting elements together. It's what powers the sun. So if you look at our anchor things over on the wall, everybody look back there, you think this is random stuff. No, this is all to help you remember. Do you see the sun and the fish? Okay? The sun is to help you remember that in nuclear fusion, hydrogen are being fused to make helium. So everybody pretend like you have a hydrogen in one hand, hydrogen in the other hand, and you squish them. You fuse them together to make the sun. Okay, everybody got hydrogen, hydrogen, squish it, sun. This is fusion. Now fission is splitting the atom. Do you see the fish? We're going to split the fish. Everybody imagine the fish. Your hand is the knife. Split that fish. Fission is splitting the atom. Both of them release nuclear energy, but it's different. Splitting the atom is used in nuclear bombs. My husband kept saying, you should put Hiroshima over there and a big nuclear bomb. And I'm like, no, that's not very nice to look at every day. We're going to put a nice, cute little fish instead. So fission is splitting the atom. Fusion is putting them together. Got it in your head? That's on the test. Okay, so we have our fish. Do you have a fish over there on yours? Nuclear fission. For some reason, my fish isn't there. Or fusion. Both make tremendous nuclear energy. Okay, the next scientist to come along, Enrico Fermi. I just like saying his name, Enrico Fermi. He's got a great name. Okay, he was the first person. Okay, so actually another scientist comes in here first. Okay, so this is during World War II. So Germany, just to review history, went to war with the world in World War I and almost won. So now it's World War II, and Germany is going to war not with another country, but with the world, and it's close. So there's a comedian, Norm Macdonald, and he says, I think they should have lost their right to be a country after doing that twice, but they're still a country, right? So it's close. We're not sure we're going to win. It's very close. Hitler is attacking the world and winning. So they figure this out. When the atom is split, it reduces a tremendous amount of energy. So immediately scientists realized this could be used for a bomb. And America started working on a bomb to defeat Hitler. All these scientists were invited to the Manhattan Project, have you heard of it? To make a bomb to defeat Hitler. Okay, there's a video that if there's time, I show. We might watch it this year, we'll see. So to go make the bomb, they invite Einstein. He's one of the ones who was invited. But Einstein too is Jewish. He is an agnostic Jewish person, meaning he's not a practicing Jewish person, but he's Jewish by ethnicity. He's not even agnostic. He agrees there's a God if you read his writings, but he's not all into the Jewish religion. Okay, everybody got that? But this is what he said. He said that the Jews have historically been persecuted. If we make this bomb, someone will try to, it'll be great because we will defeat Hitler, but one day someone will try to use it on the Jews, and I'm not going to be a part of that. So Einstein refused to be part of the Manhattan Project. It's almost like he's psychic. What's in the news today? Pull up today's news. It is that Iran, Biden is working to do a new deal with Iran, but the deal is we want Iran not to have nuclear weapons, not to have the bombs, because Iran has said if they get the bomb, they're going to blow up Israel. That there's this thing they say from the river to the sea, and what they mean is no Jews from the Jordan River to the Mediterranean. They want to kill all the Jews in Israel with the bomb. Isn't that So Einstein was pretty smart figuring out if they made the bomb, somebody was going to want to bomb the Jews, because that's in the news today. Today's news is Biden and Iran working out this nuclear deal. They had it under Obama, but then Trump ended it, and now we're going back to it again. And it's all about whether or not, but what they are saying now is that Iran actually has the bomb already. So I don't know, but it's in the news. It's where all of this science and news and history go together. So I think it's interesting. Okay, so Enrique Fermi. So they're making the bomb, but to make the bomb, you have to have something called a chain reaction. A chain reaction. So we're going to do a lab where we're going to set up dominoes, and one domino will hit down 2, and 2 will hit down 4, and 4 will hit down 8, in an expanding reaction. To have a nuclear bomb, you need a chain reaction. But when they were making the bomb in the Manhattan Project, they didn't know if they started it, if it was going to blow up the whole world. There were some scientists who thought if they did it, it was going to catch all the oxygen on the earth on fire and burn up the earth in fire. And they did it anyway. That shows you how scared of Hitler they were. They did it anyway. They made the bomb. Fat Man and Little Boy. So the first part, he was part of this, what led to the making of the atomic bomb, Enrico Fermi, because once they controlled a chain reaction, then they could make an atomic bomb. And we're going to learn a little more about that. Okay, so now that's the history. Let's talk about a little more details about the atom. The atom is made of protons, neutrons, and electrons. What is the charge of a proton? Positive. What's the charge of a neutron? Not negative. Neutral. No charge. And what's the charge of an electron? Negative, so don't mess that up. There's more subatomic particles, quarks, mesons, gluons, all of that sort of stuff that I learned about in physics class. I don't think they teach it here, but you'll probably learn about them in physics class in college, if not here. Okay, so but these are the main ones we're going to deal with: protons, neutrons, and electrons. Okay, now protons are big, neutrons are big. Electrons are very, very, very small. So small that their mass does not even count toward atomic masses. Okay, so we're going to be doing some homework on that, and we're going to be working on that in our lab in the computer room tomorrow. Okay, so I told you were going to learn how to do Bohr models. Let's learn how to do Bohr models. Okay, we'll have to use this periodic table to do them. Okay, so the first one, hydrogen. See if I can pull this down where y'all can see it more. There it is. People on the front row, maybe y'all can see it. Can you see what that little blue number is? 1. That means hydrogen, the whole number, means hydrogen has 1 proton in its nucleus. So to do its Bohr model, I draw a proton for the nucleus. And if it is neutral, that means its protons and electrons add up to 0. Protons are positive, not neutrons. Electrons are negative. So what is 1 minus 1? 0, that's what we want. 1 positive, so we need 1 negative, 1 electron to make it neutral. So that is a model of hydrogen. 1 proton, 1 electron on its quantum level orbiting around. Does that make sense to you? We'll do more and they'll get better. Okay? People who have good eyes on the front row, what's the number for helium over there? 2. So we're going to do helium. Helium gets 2 protons in its nucleus. Okay? And it gets, so hydrogen's 1, helium's 2. How many electrons does it need to balance out those 2? That's right. So they don't like each other. They're both negatives, so they're going to oppose each other. They're on different sides there. Okay, let's try lithium. What is lithium's number? 3. So they get 3 protons in its nucleus. Now, don't do it yet. How many electrons is it going to need? 3. Now, remember I told you that Niels Bohr figured out that the electrons can only hang out in certain levels. Well, only a certain number of them can hang out in each level. the first level can only have 2. So the next electron has to go up into the next level. The first level can only have 2. Lithium's number 3. Let's try beryllium, number 4. Okay, so how many protons? 4. And there's different ways to do this. I'll probably show you on the next one. Okay, so there's my little nucleus. On my first level, how many electrons does it get? 2. And how many on the next one? 2. Okay, boron is 5. And another way to do this is you say protons 5. Now later we're also going to tell how many neutrons it is, but we're not bothering with that yet. So I've got 5 protons in the nucleus. How many electrons go on the first level? 2. Okay, the second level also only takes 2. So we have to go to a third level for our next one. Okay, feeling all right about this so far? So try carbon. Try carbon by yourself. So protons is 6. Neutrons, we're going to go back later and tell what those are. How many for the first level? 2. How many for the second level? How many for the third level? 2. And they wouldn't exactly line up like that. Okay, now Bohr models only work to about element number 20. After that, remember this is 1913 science we're doing, over 100 years old. So after that, they don't work that much, but we're going to go into them a little bit more. We're going to do an activity with them next week. Yes, Melanie?
How come for like boron and carbon, they don't have two levels, and then three and 4 neutrons on the second one?
I didn't tell you about the neutrons. We're going to talk about
the electrons. My bad.
The electrons. Because we're going to talk about that more in Unit 3. Unit 3, I'm going to explain it to you more. It has to do with something called orbitals that we're going to learn about in level 3 and how they fill. We're going to get back to Heisenberg and his uncertainty principle. Okay, right now we're just laying the foundation, then we're going to build on it. All the chemistry is going upstairs. All right, ions. So you've learned about atoms, atoms that have the same number of protons and electrons. They're neutral. But not all atoms are neutral. They can gain or lose electron and become charged. Okay, we're feeling all right with this new concept? Ions, okay? If an atom loses an electron, okay? So imagine if this hydrogen lost that electron. Would it now be positive or negative? Positive, because it wouldn't have any negative to balance it out. So if an atom loses all electrons, it becomes positively charged, and it's called a cation. Because cats are wonderful, positive little creatures. We love kitty cats. Just put it in your heart so you remember this, whether you do or not. If an atom gains an electron, say we put an extra electron here on this hydrogen, what charge would it have? Negative, because it'd be more negative than positive. Do you follow that? If an atom gains electrons, it becomes negative, and then it is called an anion. Now we might fuss about whether or not cats are positive or negative, but we can all agree that fire ants are negative, right? We live in Georgia. You're standing out in the yard doing the fire drill, and in a minute you're getting bit. Right? At my old classroom, I used to be over there where Miss Foster is. There are fire ant hills out there, and they would come into the classroom and bite the kids in chemistry class. We're in the better side of the hall now without the fire ants. I haven't seen any out here. So this is what I have for you to remember this. You're going to learn what these ions have to do with the periodic table. Here's our anion, negative, terrible anion. And here's our sweet, darling, positive little cation. Okay? This is going to help you remember it for the test. My songs, my dances, my drawings, They all help, I promise. Helps get it in your memory. Okay, any questions about that? Cations, anions, we all agree we hate. Look how good my son did drawing that ant though. I think it's the best thing he drew up there. I just think that's a great ant. But remember, he's terrible. He's negative. Okay, that's my son Josh. He's good at drawing. Where's my thing? Oh, there it goes. All right. So this is what your homework is, the worksheet. So you can get out that worksheet if you want to. Look at the homework worksheet as you do this. So hydrogen's name is hydrogen. Its symbol is H. Okay, so write this down as you go in your notes, but also look at the homework. Okay. We are going to write down everything we know about it. Hydrogen's symbol is H. It has an atomic number of 1, meaning it has 1 proton. How many protons does it have? 1. How many neutrons? How you get the neutrons is you subtract the protons, the whole number, from the decimal number. So 1 minus 1.00795 rounded off is 0. Does that make sense to you? You subtract them, then round it off to a whole number. So my number of neutrons is 0. The mass is this rounded off to a whole number. 1.00795 rounded off to a whole number is 1. It's also the number of protons plus neutrons. 1 plus 0 is 1. The number of electrons is the same as the protons as long as it doesn't have a charge. If it has a charge, a plus or a minus, you have to figure out if it gained or lost and how many. Okay? And then is that atom or an ion? It's an atom because it doesn't have a charge and its charge is 0. Okay, let's do the next one. I always give you a clue. So here the symbol is C. What is the name? Carbon. Let me write. Here it goes, carbon. Okay, on the periodic table, what number is carbon? You see the whole number there? It's 6. See the blue 6? Okay, so what's its number of protons? 6. Atomic number is the number of protons. Number of neutrons. What is 12 minus 6? 6. So I did that once and somebody said, look, chemistry is evil. 666. What is the atomic mass? What's 6 plus 6? 12. The number of electrons, it doesn't have a charge, so it's the same as the protons. 6. And it's an atom because it has no charge. Okay. So what about atomic number 13 is my clue. I look over here at 13. It's aluminum. So I say Al, aluminum. Okay, its number of protons is 13. Its number of neutrons, I gotta look at this, is 27 minus 13. What's 27 minus 13? 14. So mass is 27. Number of electrons is 13 because there's nothing to tell me this has a charge. It is an atom with no charge. Okay, so now we get to a more interesting. What's number 16? Do you see it over there? It's sulfur. Symbol S. S-U-L-F-R, sulfur. Spell it like they did. Yep. Sulfur. It's a U. Doesn't look very U-y. All right, so its number of protons is 16. Its number of neutrons, we look and we see that sulfur is 32. So what's 32 minus 16? 16. So the mass is 32. Now notice the electrons is 18. So is it an atom or an ion? It's an ion. Has it gained or lost electrons? How many? So what's its charge? Minus 2. It gained 2 negatives. Electrons are negative. So I put a little minus 2 right there. That's where the charge goes. It goes as an exponent with its positive or negative on it. How do we feel about that? Is that good? Okay, so helium, I'll let you try that one by yourself later. That one's easy. Okay, so ions are charged electrons. Now, one of the things that makes this hard is isotopes also start with the letter I. So we have to get isotopes in our head. Things that might help. Isotopes often show whether or not an element is radioactive. When you're talking about isotopes, a lot of times it's radioactive. So where you've seen isotopes is if you've watched The Simpsons, the cartoon, the ball team is the isotopes because, you know, they have the nuclear power plant there and the three-eyed fish and all that. So isotopes have to do more with radioactive things. So atoms can have more or less neutrons. They can be fat or thin. So here's our little anchor chart for that. Here we have these wonderful positive cations, but now they're going to stand for isotopes. Are they both cats? So they're both cats. The difference is we have fat Ruby and skinny Tigger. Now these are my cats. They eat the same thing. Ruby is very fat, Tigger is very skinny. The difference is Tigger runs all over the house like a madman, exercising, and Ruby likes to lay on shoes. She finds some shoes and lays on them all day. So no exercise. I think it's a great little cautionary tale that you need to exercise. Because poor little Ruby, she's so fat. And it's because she never exercises. Sometimes she'll chase a Nerf dart tag, but not usually. Okay, so there's Ruby and Tigger by isotopes. Okay, so some isotopes, especially the fat ones, can be radioactive. So there's this connection between radioactivity and isotopes. What radioactivity is that the atom falls apart. It's too big. It's got too many neutrons and it falls apart. And it'll give off radiation. That radiation has names, alpha, beta, and gamma, and there's other kinds of radiation. And so there's a couple of things I want you to know. How you write different isotopes is like this. So carbon has some isotopes. One is carbon 12 and one is carbon 14. Yeah, there's actually a carbon 13 too. But you write it like that. You write the word, then a dash, then the number, and that number is its mass. Okay, that's the mass of it. The other thing is I want you to know, do you have something here to write these? Do I have it? We're going to go into it more later. But I'm going to show you some things about this, okay? A symbol for alpha looks like a little fish there. Beta symbol is a big B that you don't close at the bottom, a big curly B with a tail. And gamma looks like horns. Like, isn't that Aries zodiac sign? Something like that. Sometimes they're written like this. Alpha will have its mass of 4, its number of protons 2, and the alpha sign. Beta will sometimes have a 0, -1 beta, because it's actually an electron. And gamma will sometimes have a couple of zeros, because gamma has no mass. It's just high energy. And then sometimes alpha has the 4 and a 2, and then the helium sign, because helium is number 2. Beta sometimes has the 0 and -1 and a lowercase e to stand for electron, because beta particles are actually electrons. So we're going to do more of that in Unit 3, but I wanted to introduce it to you because I think it might be in your computer lab tomorrow. Okay, can I scroll? All right, so the last thing on this test is you have to know the areas of the periodic table. So y'all were saying this in your report. You were saying it's a halogen, it's a lanthanide, it's a transition metal. All of you said it. Now you need to know what it means. It means where is it on the periodic table. So we're going to color these. You need to color it on your periodic table. Okay, so what we're going to do first is get yellow. up here. Oh, what did it say? I want to thin this here. All right, and there is a division between the metals and the nonmetals, which is a stair step. And I want you to draw that on first. It goes like this. Okay, this separates the metals and the nonmetals. Okay, so first of all, draw that. I'm going to write non-metal, and I'm going to write metal. And the difference is that line, okay? Metals and non-metals. That's the first thing you have to know. Yes? You get 2 passes, but it's too late. Could you go to the nurse instead? I can let you go to the nurse. The passes are in the box. Get one out and sign it. Okay. And hand it to me, I'll sign it. Okay, so metals and nonmetals, you got that. Next is metalloids, and the metalloids, we'll use red. The metalloids are the things that touch the metal-nonmetal line. So they're a little like metals and a little like nonmetals. So I want you to like draw some little lines through those. These are the metalloids. Are you a metalloid? We're going to say you're a metalloid. All right. Okay. All right, so color code, by metalloid, scroll back up and draw some of those hash marks by it. Yes?
No way you could zoom in.
We'll try. If you'll get, it gets a little bigger. The only thing is I can't use. All right, so just make sure you're making your key. You're not just coloring, you're making your keys. Okay, the noble gases, what color do we want them to be? Let's make them, we'll make them nice sky blue. That seems kind of royal, doesn't it? Oh, we should do them purple. We'll make them purple because they're royalty. Okay, the noble gases are this column right here. So notice that OG is both a metalloid and a noble gas. Things can be more, and a non-metal. Things can be more than one, okay? The halogens, those are the salt formers. I'm going to color them green because chlorine is a green gas. So this is the halogens. Notice these are halogens and metalloids, both. So those are the halogens. I'll put an H there so y'all know those are halogens, and we'll put an N for the noble gases. Okay. Whoops, that didn't do it. N for noble gases. Okay, the alkaline metals are this first family over here. We'll make them light blue. These are the alkali metals. Okay. The alkali earth metals, we'll make pink because I like pink. The alkali earth metals are this next column. The transition metals, what color shall we make them? They can be gold. And that's too much like our other one. Let's make them gray. Okay, so our transition metals are these in the block right here. Just to there. Nowhere else. I'm going to make all of those. Thank you for letting her back in. So those are the transition metals. Notice they stop right there. Okay, so these right here are other metals, and those are other non-metals. Okay, the actinides, we'll make them crazy. I'm going to make them rainbow colored. The actinides are these on the bottom row. And how you know it is notice that it's actinium right there. The lanthanides, I'm going to make them, I guess we'll go with gold. Well, they're too much like the actinides. Let's make them that color of purple. Okay, notice that it says lanthanum, so these are the lanthanides. All right, you gonna be able to do that on the test? We did awesome. Look how we finished before the period was out. Yay, yes. All right, like, share, subscribe.